Okay, grade 11s, we are here with another video, Euclidean. Again, I'm going to be covering a question that has to do with cyclic quads. It has a tangent, and this question of this video, you're going to understand how to interpret Euclidean questions effectively when you've been given numerical values. Because in this question, guys, we're dealing with angles. We're dealing with angles that actually have numerical values. So, guys, as always, let's get started. Let's look at 9.3. PQR is a tangent to the circle QEFGH. EF is parallel to QH. FG equals to GH. Let Q3 equals to 30 degrees and H3 equals to 70 degrees. Now, before we begin, guys, we always need to annotate our diagram. Now, tangent. We're going to write down a few of the Euclidean theorems that specifically applies to your tangent, right? A tangent line. So what do we think of, guys? We think of tan chord, right? We think of tangent perpendicular to radius, right? We think of tangents from the same point. Now we're going to go ahead and actually annotate this onto our diagram. So guys, please remember that PQR is a tangent. PQR. Let's first look at tan chord. So how does tan chord work, guys? The very first thing you need to do is you need to identify your tangent and you need to identify the chord. Okay, so what is a chord? Remember, guys, a chord is just a line that divides your circle into different segments. Your segment would just be a space. Your chord is not the same thing as a radius. Please remember that. Okay, so EQ is close to our tangent, and EQ is a chord. As you can see, it cuts the circle into a segment, right? And it's not a radius, obviously, right? So we're going to highlight that part. Now, the angle between the tangent and the chord is Q1. You can clearly see it's Q1. So how the tan chord theorem works is that the angle between the chord and the tangent is going to equal to the angle that chord subtends. So how do we find out what angles it subtends? And you can check that on the previous video. I already explained that. But what you want to do is you want to take a little pencil. You want to start tracing the lines that stem from the chord all the way to the other end of the circumference of the circle. You trace it, it ends over there. Do the exact same thing on the other side. Trace it, it ends over there. Which the chord EQ subtends angle H3, which is 70 degrees. So what does that mean, guys? That means Q1 is going to equal to 70 degrees. Okay, so Q1 equals to H3. So I'm just going to already label that as 70 degrees, right? So we don't get confused. Now, where else does tan chord apply? On the other side of the tangent, guys. Now, please remember, tan chord theorem applies to different parts of your tangent, not just like the entire thing. Look for a part of your tangent and then look for your chord. Now, what chord is close to your tangent? It's HQ. What angle is between HQ, guys? The angle that's between HQ and the tangent is Q3, which is 30 degrees. The next thing that you need to do is you need to identify the angle that the chord subtends. How do we do that? You're going to take your pencil and you're going to trace the lines that stem from the chord all the way to the other end of the circle. So if we trace it, it ends over here. Do the exact same thing on the other side of the chord. Trace it. It ends over there. So that means that QH, the chord subtends not H2, sorry, E2. So what does that mean, guys? Please make sure you use a different color. Well, that means that Q3 will equal to E2. And just like that, we're actually done with tan chord, right? So now let's look at tangent perpendicular to radius. Now, this theorem over here is not going to apply. Why is it not going to apply? Because we need a tangent and we need a radius, guys. We don't have a radius. Why is that? Because there is no center, guys. Okay, if they didn't say anything about there being a radius, not even a radius, if they didn't mention anything about there being a center of a circle, there's not going to be a radius in general. Okay, so we can just immediately forget about that. What about tangent from the same point? That's also not going to work. So when it comes to tangents from the same point, guys, you need two tangents that meet at the same point. Okay, in this case, we just have one tangent. So no, that's also not going to work. Okay, so now let's continue on. They tell us that EF is parallel to QH. Okay, so they tell us that EF would be that line over there. Let me just go back and mark this off again. Okay, so they tell us that EF is parallel to QH. So now, guys, when we see parallel lines, what are the few rules that we think of? You need to write this down. We think of alternating angles, we think of cointerior angles, and we think of corresponding angles. So we're just going to go back and look if this actually applies to this question, right? So When we're using alternating angles, guys, you need to look for that diagonal line that connects those two parallel lines. And if you see two angles that are in that alternating position, those two angles will actually equal to each other. Okay, so for instance, Q1, that diagonal line we can clearly see is EH. So we know that E1 will actually equal to H3. So it looks like we have common angles already. So since E1 equals to H3 because of alternating angles, that means E1 is going to equal to 70 degrees because H3 is equal to 70 degrees. So we're just going to go back and label that onto our diagram. Okay, so in this case, guys, when it comes to cointerior, we're just going to keep cointerior in mind just in case we need it. We're just going to write that down. And what about corresponding? Corresponding is not going to work in this case. Why is that? Because we need to identify an angle that comes before one of the parallel lines. In this case, we don't have an angle that comes before um, any of the parallel lines. It has to look exactly like this, guys. You have to have a straight line. You need to have your parallel lines. Okay. That line doesn't always have to be there, by the way, guys. You just need to have your two parallel lines, one angle before the other parallel line, another angle after the another parallel line, and that's where it's going to apply. In this case, it's not going to work. Okay, so there isn't an angle that comes before EF. There is an angle that comes before GH, but you can clearly see it's skewed. Okay, it's skewed. So yeah, that's definitely not going to work. Okay, so now, guys, let's continue on. So we're going to actually start off with the question. Now, let's look at question 9.3.1. Calculate Q1. So we said that Q1 equals to H3. We've even marked them off as being equal. Q1 equals to H3 because of tan chord theorem, right? So be very careful when you actually write down your reasons. You need to say that PQE state. Don't just say Q, guys. You're going to get that completely wrong. You have to state, you could just say Q1 equals to H3 because equals to H3, which is 70 degrees because of your tan chord. Therefore, Q1 will equal to 70 degrees, and that's all you have to add. And then you're just going to annotate that onto your diagram. Then for 9.3.2, prove that G equals to 110 degrees. Now, where do we start, guys? This is so important to remember. And actually, before we begin, we skipped something. We can clearly see that GF and GH are equal to each other. So we have an isosceles triangle. Please remember that anytime you have an isosceles triangle, we always think of opposite angles equal sides. We know that E2 will equal to H1 because of opposite angles equal sides. Okay, so guys, when you have, and this is something that we also before we even continue on, guys, we can actually see that we have cyclic quads that are a part of this diagram, guys. We have you can clearly see that EFQH is a cyclic quad. Okay, we can also see that FGHE is a cyclic quad. You can clearly see it's four-sided, and all four sides land on the circumference of the circle. So what we want to do is we're quickly just going to write down a few of the theorems that directly relates to a cyclic quad. Opposite angles of a cyclic quad are equal to 180 degrees. Angles in the same segment and exterior angle of a cyclic quad. Okay, so now let's first look at opposite angles of a cyclic quad are equal to 180 degrees. Now this theorem is going to be very helpful because we actually have angles. We have angles that have numerical values, so we're just going to keep that in mind. If you want to calculate G, you can think of this. If you want to calculate E, F, H, any angle that is on the circumference of a circle and that's part of a cyclic quad, that there is a possibility of us actually using that theorem. What about angles in the same segment? That isn't going to work, guys, because we don't really see that bow tie shape. Okay, so since we don't see that bow tie shape, we know that's not going to work. And then what about exterior angle of a cyclic quad? No, guys, we do not see any exterior angle that is outside of any of the cyclic quads. So yeah, that's also not going to work. So the only one that we're going to be focusing on would be opposite angles are equal to 180 degrees. So what happens? Where do we start? That's what a lot of students ask. Where do you start? So since we haven't been able to connect G to any other angle, you can see that it isn't colored in. Since we can't connect G to any other angle, we start thinking of other options, right? We start thinking of sum of angles of a triangle. We think of exterior angle of a triangle. We think of vertically opposite angles, and we also think of angles on a straight line. Just write this down for yourself, guys. You need to write down a list. Very important. But G is a part of a cyclic quad. We have to remember this, guys. If G is a part of a cyclic quad, please remember that the very first option you should be thinking of is trying to use opposite angles of a cyclic quad are equal to 180 degrees to try and solve for G. Okay, so if we were to use opposite angles of a cyclic quad, So please remember, guys, you need to look at the angle that is opposite from G, because we know that G is a part of the cyclic quad FGH. Now, what angle is opposite from G, guys? It is E. And remember, we said that E was equal to 70 degrees because of alternating angles. We said that E is equal to H3 because of alternating angles, and that is literally that simple, guys. We already have our answer. Okay. So now what you want to do is you want to go back and first state that E was equal to H3 because of alternating angles, and you need to state what lines were parallel to each other. Okay, the lines that were parallel to each other was EF and QH. Then we're going to use opposite angles of a cyclic quad so we can finally find out what G is equal to. You're going to first state that E1, which is 70 degrees, plus G equals to 180 degrees, and your reason is going to be opposite angles of a cyclic quad. You're going to take it over onto the other side, giving us 110 degrees. And what you want to always do is you just want to go back and annotate that onto your diagram. Annotate that as 110 degrees. Okay. So you want to go back and annotate that as 100 and okay. Go back and annotate that as 110 degrees. The next thing is we have to calculate F1. So let's look at F1. Where do we start, guys? Please pay attention. We haven't really connected F1 to any other angle directly using our, generic Euclidean theorems like opposite angles of a cyclic quad. Sorry, not opposite angles of cyclic, like tan chord theorem, etc. But if F1 is a part of a cyclic quad, the very first rule that we have to try and see if we can use would be opposite angles of a cyclic quad are equal to 180 degrees, okay? So we first have to start off by identifying what cyclic quad that it's a part of. So it's a part of the EFQH cyclic quad. What angle is opposite from F? It's Q2. So we first have to find out what Q2 is equal to, and then we're going to be able to use opposite angles of a cyclic quad. Now, look at this, guys. Q2 is literally part of a straight line. It's very important to look carefully. It's a part of a straight line, and all the angles that are a part of that straight line have values. So we can use angles on a straight line to find out what Q2 is equal to. Okay, so how does angles on a straight line work again? Just to refresh your memory, let's go over that real quickly, okay? So angles on a straight line. We have Q that has been divided into three parts. We had Q1, we had Q2, okay? Q1, no, Q2 should be over here, and Q3. Okay, so you just need to add all of the angles that are on that straight line and equate it to 180 degrees. So Q1, for instance, equals to 70 degrees. Q2 is literally what we're trying to look for. Q2 is what we're trying to look for. And then Q3 is equal to 30 degrees. Okay, and you just want to equate that to 180 degrees. And then you're going to take everything over onto the other side so that you can get to your answer, okay? And then once you do that, your answer is going to be 80 degrees. So now we actually know what the value of Q2 is equal to, guys. It is equal to 80 degrees, right? So now we can easily just say that F1 plus Q2, which is 80 degrees, equals to 180 degrees because of opposite angles of a cyclic quad. It's literally that simple. Do you see how we solve for that so easily? So then you're going to go back and say that F1 plus Q2 equals to 180 degrees because of opposite angles of a cyclic quad. You're going to take that number over onto the other side and isolate the F1 because that's what we're trying to look for, giving us an answer of 100 degrees. And that is exactly how easy and simple it is, guys. Go over this question over and over again, and I promise you, by the time you write your exams, Euclidean is going to be so, so easy. Okay. Okay, guys, so we've come to the end of the video. Make sure you go over this question again. We have lots more in store for you, a lot more content, a lot more questions that are going to be incredibly helpful. But as for now, we'll see you in the next video.